Hey everyone, today we're going to be going over the 2020 AIME 2 question 15. So let's get started. Let triangle ABC be an acute scalene triangle with circumcircle omega. The tangents to omega at B and C intersect at T, and let x and y be the projection of T onto lines AB and AC respectively. Suppose that BT equals CT equals 16, BC equals 22, and tx squared plus ty squared plus xy squared was equal to 1143. And so the problem asks us to find xy squared. So right from the get-go, the first thing that we can notice is that this this condition that the problem has given us is really strange and really specific. It gives us a lot of squares, and it's also the sum of squares, so we know that there's probably going to be some type of computational formula at play here, which involves squares. And for those of you who are familiar with Stewart's, it might remind you of Stewart's almost immediately because of the squares. And so we might be motivated to try using Stewart's. So I've drawn this point here because and I'm going to say that this point is the midpoint of the segment XY of this segment, the black segment here, because of we sort of want to just find a formula which is really similar in style to this. At this point, we're not exactly sure what we're going to get, but right now we're just playing around to see if anything interesting happens. And so those of you who are familiar with Stewart's, if we want the most amount of terms to cancel out, the most natural thing to do is to take the median and to whatever side, in this case xy, and use Stewart's with respect to xy in triangle TXY. And the reason we're using triangle TXY is because of the segments here, TX, TY, and XY, which are given in the problem conditions. So let's say we call the midpoint of XY as O, and let's see what happens when we apply Stewart's. So we have man plus dad is equal to BMB plus CNC, which is Stewart's in whichever form that you guys are familiar with. And so we have a couple of relationships here as well, because we've specifically chosen O to be our midpoint. We also have that XO is equal to OY, which is equal to 1/2 times XY. So the first thing we can do is, we can multiply both sides by 1 over XO, because each term has some common factor XO. And moreover, we can replace each OY in terms of XY, because ultimately we want to have something in terms of TX squared, TY squared, and XY squared, and we don't really want to involve XO or OY at this point. So after plugging these in, we have this term, we will cancel an XO here, and we can replace OY with 1/2 XY. So our very left-hand term becomes XY squared over 2. And the middle term, this XY cancels with this XO to get 2 times TO squared is equal to both of this XO and this OY cancels. So we get TY squared plus TX squared. And this is pretty much what we wanted, because we see that TY squared plus TX squared is actually given to us here pretty nicely as 1143 minus XY squared. So let's replace this with 1143 minus XY squared. And in fact, we can solve for this equation because now we have one equation in terms of XY squared and TO squared. So now this is really useful to us because now we know that our problem has pretty much reduced down into finding the length of this segment. But now, unfortunately, we're stuck. How exactly should we go about finding this segment? Well, one of the key things, which is really always important in geometry, in any geometry problem, is to draw a really solid diagram. Because in this case, the key to finding out the length of this segment, OT, is to notice that when we reflect t over point O, let's call it t prime, then t prime is actually the base of the altitude from t in triangle BCT. That is, we can find TO because we can find TT prime by the Pythagorean theorem here. So the key idea is to firstly is to notice that, which is pretty much the crux of this problem, is to reflect t over the midpoint of xy and figure out that t prime is in fact the base of the altitude from t in triangle BCT. But how exactly should we go about proving this? Because we want to try to be rigorous here. Well, this is pretty simple once we have the idea down, is that when we reflect t over point O, note that we must have that x t prime y t has to be a parallelogram, just based on the definition of a parallelogram, because each diagonal bisects each other in this case. So in this case, we know that ty is perpendicular to ay because of our definition of y, and similarly we know that tx is perpendicular to ax by our definition of x. And so because t prime y tx is a parallelogram, then all we have to do is prove that xt is perpendicular to ay, and similarly yt prime is perpendicular to ax. And we know this will suffice. So ultimately this comes down to proving that the midpoint of BC, t prime, is actually the orthocenter of triangle AXY. And yeah, this can be pretty easily be done by some quick angle chasing. Pretty easily be proven, rather, with some quick angle chasing. So now it remains to prove that t prime is in fact the orthocenter of triangle AXY. In other words, we have to prove that angle t prime xa is equal to 90 degrees minus angle A, because angle t prime xa is here, and if t prime is the orthocenter, then we know that the measure of angle A has to be the complement of angle TXA. And now we can angle chase to try to prove this. So the first thing we should notice, let's use a different color to try to make this more clear. Angle T prime XA is actually equal to angle T prime TB, because this quadrilateral right here, BT prime TX, is actually cyclic because of these two right angles right here. And once we've established that, we know that angle T prime XA is equal to angle BTT prime. But we also know that this is equal to 90 degrees minus angle T prime BT, because T prime is the midpoint of BC and BTC is isosceles. And finally, we know that T prime BT is equal to angle A, because BT is tangent to the circle and subtends the arc BC. And angle A also subtends the same arc. So we've proven our claim. And we note that the exact same argument holds for the other side. That is, we can use the exact same argument to prove that angle T prime YA is equal to 90 degrees minus A. And thus we are done, because we know that if any two perpendiculars intersect at T prime, then T prime is our orthocenter as desired. And so this completes our proof that the reflection of T over the midpoint of XY is in fact the midpoint of BC. And now we can really easily compute TO squared, because we know that TO squared is equal to 1/4 times TT prime squared, because TO is half of the length of TT prime, and also we know that TT prime squared is equal to BT squared minus BC over 2 squared by the Pythagorean theorem. So now we can calculate, well, this is equal to 1/4 times BT squared is 16, and BC squared is 22. So we get that TO squared is equal to 1/4 times 135. Therefore, we can plug in our numbers and get that 3/2 times xy squared is equal to 1143 minus 135/2. Finally, xy squared is equal to 717. And remembering that xy squared is our desired quantity, then we have that our answer is 717. So we are done.